Example 3, determine if the series n over e to the n squared converges, diverges. So we're going to first start by expressing that the an term as x over e to the x squared. And we're going to find the area under that integral so it's going to be a limit as a approaches infinity. And we're going to start at 1 to a of x over e to the x squared dx. So this one's going to involve a substitution. Our substitution is going to be u equals x squared, and our derivative is going to be du is going to be 2x dx. Okay, so we're going to maybe move that 2 over, so du over 2 is equal to the x dx that I want to account for. Now, when we're doing this, make sure you just be careful of the notation and keeping track of your variables. So I'm going to have area equals limit as a goes to infinity of x equals 1. So remember that when we change to u, we need to state that the bounds are in terms of x. We're going to replace the x squared with e to the u, and the x dx we're going to replace with du, and we'll put the 1/2 on the outside here. Okay, so now we can just integrate this, so we end up with the area limit as a approaches infinity 1/2, and this is going to integrate to e. Since the power is negative u, it's just going to be e to the negative u, and I just account for that extra negative, so we're going to put that negative in front like that. And that's going to be, for the bounds, x equals 1 to x equals a. We're going to substitute back for the u, so limit as a approaches infinity, negative 1/2 e to the x squared. And then we can do our bounds as 1 to a, because we're back to x's in this case. So the area, I'm going to continue over here. Area is equal to negative 1/2. I'm going to substitute the a in now. E to the a squared minus, put brackets around that, e to the negative 1 squared. So I'm going to end up with, I forgot my negative in here. This is going to be a negative power there. So it's going to be negative a squared and negative 1 squared. So we're going to express this in the denominator, and I need to make sure that I keep my limits here. I need to write my limit in since I haven't done my limit yet. So limit as a approaches infinity, and then I'm going to plug in my infinity. So negative 1/2. That negative power ends up in the denominator, so 1 over e to the infinity squared minus 1 over e. And then this portion here, this is going to become 0, and I divide by e to the infinity squared is going to be 0. And so my answer works out to be negative 1/2 times negative 1 over e, so it becomes positive 1 over 2e. Okay, so again, we're not interested in the actual value, we're just interested in convergence. So this is a finite value, so then we say it's convergent. Okay, and because it's convergent, we're going to say then that the series is convergent as well. So this, since the integral converges, we know that the similar series must converge. So there is our conclusion based on the the finite value of that area. In example 4, we're going to use substitution as well. So our first thing is we're going to set up our function. Our function is going to be 1 over x log x, and our area is the limit as a approaches infinity from the bounds of 1 to a. The integral is going to be x log x, and we're going to do our substitution. We're going to let u equal log x. That lets our du equal 1 over x dx, and then we can account for that is our du. So the limit as a approaches infinity of x equals 1 to x equals a, again keeping in mind our bounds are in terms of x's, and then I do my substitution. We're going to replace the x 1 over x dx over x with du, and the log x we're going to replace with u. Integrating this, we end up with the integral is going to be 1 log of u, and our bounds again are going to remain the same, x equals 1 to x equals a, and then we're going to substitute this for log. So we're going to put the log in for the u. So we end up with log of log x. And again, keeping our bounds. Now we can convert our bounds back into x. Since we have our terms in x's, we're just going to state our bounds as 1 to a. Doing our substitution of our bounds, so we have the limit as a approaches infinity, log of log a minus log of log 1. Okay, and then inputting, so log 1 is going to be 0, and we end up with log of 0. So I'm going to do this in a couple steps. So we end up with log of log infinity. That's going to be the first part, minus log of 0. When we evaluate the log 1, that just works out to be 0. So log 0. Okay, and we're approaching, since we are approaching the 1, and we should really have a one-sided limit here, but we're going to have log of infinity is infinity. So we have log infinity minus log of 0. We're going to approach it from the right-hand side. That's going to be negative infinity. And so we end up with infinity plus infinity. That's infinite. So we know that this is divergent. Okay, so therefore, our conclusion is that the series is also divergent. Okay, so there's our conclusion. That's our integral test. We test the integral for converging or diverging. If one converges, the other must converge. If the other diverges, the other one must diverge. One thing to note here is, this is just kind of an extra, we have a 1 over n that is diverging, and we added on an extra log So although we're making the power on the denominator even bigger with this extra log n, since the log is so weak, it still doesn't increase the power. This is still less than power 1.0001. That log is a weak function. So any power on n is going to be more powerful than multiplying that n to the power 1 with an extra log n, because notice that it still diverges. Whereas if we made this 1 over n to the power 1.00001, that point it would start to converge. And that's when we use our p-series information, or what we know about p-series, where p is greater than 1, it converges. And we're going to do this in the next example.